All right, I think we're back. Let me just see. All right, I think we're back on here. Let me just... All right. So, all right, I'm going to finish this question. I apologize for the interruption here, but let's... Now I can monitor the chat. Let's see. All right, so here we go. I think this is going to work better now. I launched it from OBS directly, but it was the software I was using to write this out was lagging. It's still lagging a bit, but hopefully this fixes it a bit. So this works out to -1/2. Okay. Hello to everyone here. So we have 6 right now. So yeah, sorry about that delay. It was just... it like basically imploded. I'm hoping this one hangs on. Yeah, I don't know what the issue was, but whatever. Hopefully this one will stay with us. So this is a certain type of limit to be comfortable with. All right, now the other kind that you could deal with is when you have a piecewise function. So I'm actually just going to add a page to this. So let's see. So we don't necessarily have to skip the page, but I just want it to be ready for when we need it. So now let's say we have a piecewise function. And there's a few kinds you could have, but let's say we have something like this. P of x is equal to, and we're looking at, we have 3x minus 2. And it's when x is not equal to... Yeah, I'm not sure if this is lagging a bit on my end because I'm sharing the actual program versus just sharing the screen, because they updated OBS recently. So this is only week 2. So this is a work in progress. This is not the finished product, but I appreciate everybody for being patient. All right. So here, if we have this function, let's say we want the limit as x approaches 1/3 of this. So in this kind of limit, when you have, and let's make that a little neater, a not equal to piecewise function, you're going to plug into the not equal to part. All right, the reason being, like, why do we plug into the not equal to part? Well, for the not equal to part, let's say we look at 1/3. When x is not equal to 1/3, those are the values we could use that get us close to 1/3. So that's why when we evaluate the actual limit, we're going to plug into the part where x is not 1/3. So we're going to have 3 times 1/3, and then we're going to have minus 2. Okay, so then this is going to cancel, and it's going to give us 1 minus 2 is -1. But now let's say if we want to determine if this function is continuous, we would have p of 1/3, and that's equal to 4. So this right away is jumping out at me that this is not a continuous function. And the reason being is that the limit as x approaches 1/3 of p of x is not equal to p of 1/3. So this is the definition of continuity, specifically at x equals 1/3, and that'll tell us that our function is not continuous there. All right, so something to, pay attention to. All right, wow, we got 9 people here, so hello. Let's see, the camera itself. Is this... Oh, maybe I got to request high definition because right now I have it in. Oh, there we go. I could put this in HD from. Yeah, I'm just trying to monitor this, that people could hear me and that it's sharp. All right, yeah, you can see the green screen behind me is not perfect. Like my hand will disappear. So I'm working on it. But right now I think it looks pretty decent. Then I'm just going to try one thing. So I'm going to do some behind the scenes stuff here. So instead of doing, maybe if I share it like this, if I do another screen capture, I'll delete this if it like ruins everything. Application capture, just window capture. Yeah, I'm going to cancel this. Cancel, cancel, cancel. And yeah, this, I'm just going to throw that one in the garbage. All right. Yeah, so we're back. Yeah, I'll mess around because I just want it to lag a little bit less on my end. This program feels like it's running very slow for some reason. But last week it was flying. But I don't know, maybe because I have some other stuff here that's making it run slower. But whatever, we'll just have to make do. All right, so any other topics that we want to see specifically? So far we did limits, continuity. I think people from my actual class said that they wanted to see, you know, topics that are for tomorrow's test. So I'll pull up more questions here. Now, if you're trying to find or explain why a piecewise function is continuous, let's come up with one where I'll come up with a different kind. So let's say we had f of x equals, and we have a piecewise function like, let's say 2x minus 1 when x is less than or equal to 0. And then we have, let's think of a nice one. So 2x minus 1 when x is less than or equal to 0. And I just want to pick one that's maybe a little bit more exciting. But whatever, I mean, this will do the trick. And then we have 4x minus 1, something like this, when x is greater than 0. So if we want to say like we want to determine is f of x continuous at x equals 0. And let's say we want to explain this. Okay, so we want to explain this as if it's the AP test and we want to get full credit. So for this one, you have the limit as x approaches 0, but notice it's a less than greater than situation, less than or equal to greater than situation. So what we're going to do here is we have to find the left side and the right side limit. So for something like this, let's go out here. This is our thought process. Just know that x less than 0 or even less than or equal to 0, either one, corresponds to x approaching 0 on the left side. So if we're approaching 0 from the left, we associate it with the top piece and we plug in 0 to the top. So we'll have 2 times 0 minus 1, which is equal to -1. And now we found the left side limit. We're going to find the right side limit. So we have the 0, x approaches 0 from the right side. And for a situation like this, now we're plugging into the greater than piece. We're going to have 4 times 0 minus 1, which is also -1. So now we have to draw our conclusion. And our conclusion here is that these limits are equal. So we could say, therefore, the limit as x approaches 0 of f of x equals -1. However, we also could say here that the function value at 0, if we look, we move up, see when x is less than or equal to 0. So if we want to find f of 0, we would plug 0 into the top piece. So we plug it into 2 times x minus 1. So you're going to have 2 times x equals 0 minus 1, and that's equal to negative 1. So now conclusion, is f of x continuous at x equals 0? Absolutely. It is absolutely continuous. Okay? So f of x is continuous. All right, this leg is hurting my soul a little bit. All right, so f of x is continuous at x equals 0. And the because, sorry if I said at x equals negative 1. The limit and the function are negative 1, but f of x is continuous at x equals 0 because, and now we just connect everything by the definition of continuity. We have the limit as x approaches 0 of our function f of x. So the limit of our function is equal to the function value at 0. Okay, and that explains it. Just know for the AP test, I know it's far away, but this is the $1 million definition for continuity. This definition is so important, okay? The limit as x approaches c of f of x equals f of c. If you could show this is true, if that's true, then your function is continuous at x equals c. All right, so really big idea. Big idea to master. All right, cool. So anything else specifically in the chat? We got a few people. Please, if you got something specific, just type away. Let's see what, okay, so we're at 8:55, so we have some more time. So I figured I could share the wealth. If anyone's here for some non-calculus questions, ask away. Limits to infinity. All right. Limits to infinity. So with limits to infinity, when I think about those, I think about the race to infinity, and it's the numerator versus the denominator. So just know, if you had something like this, the limit as x approaches infinity of, let's say, x squared plus 1 over, and then we have x to the third, like minus 2. I know right away this is 0 without thinking very much. And the reason being is the denominator wins the race to infinity. And it's all about the leading term. So x to the third beats x squared and 1. So if the denominator wins, the limit goes to 0. All right, so this is just an idea for limits at infinity. So limits at infinity is that if the numerator, this is like kind of like informal notes, is less than the denominator, and we're talking about like the degree. If the degree of the numerator is less than the denominator, then the limit goes to 0. Okay, so that's just like something you could answer really, really quickly. The second case that you could run into is you have a limit as x goes to infinity, and let's say it's a tie. All right, or we could even say this one first. Let's say it was flipped, x to the third minus 2 over x squared plus 1. There's sort of this helpful theorem that you only need to focus on the leading terms. So you see how the leading terms are x to the third versus x squared. So now I know this is going to infinity. But the reason being is that this is the limit as x goes to infinity of x to the third. Let's make that neater. So let's see, eraser. So we have x to the third over x squared. Okay, let me just put my phone on silent so my loud ringer doesn't interrupt stuff. So, all right. So this here, the reason being is that if I had to show another step, so let's just say I'm kind of jumping ahead there by saying that. So let me just add another page and we could see. All right. So here we could say it's because this is the limit as x goes to infinity of x to the third over x squared is x. And now it's just obvious, like as if it's just x and the limit as x goes to infinity, then this is just going to go to infinity. So the idea for this, and I'll drag these notes with us. All right, yeah, this is kind of difficult when it's lagging. So, oh, this is going to be stubborn. All right, I'm just going to copy this first. I'll just paste it. All right. And here we go. So a second point to make is that for limits at infinity, you're going to have that if the limit's at infinity, if the degree of the numerator is greater than the degree of the denominator, then the limit could actually go towards plus or minus infinity. I don't want to say that it goes automatically to infinity, because all I'd have to do is put a minus in front of this, and now it would become minus x to the third over x squared minus x, and then it would go to minus infinity. All right, so this is just a big idea, though, that it's going to go to plus or minus infinity if the numerator has a higher power of x. But probably the most helpful idea is that when you have a messy polynomial, if we make up another one, like the limit as x goes to infinity, and let's say it's like, I don't know, 2x squared minus x to the 10 plus x to the 5th over x to the 5th plus x to the 8. Something that's like in messy form is that you only have to look at the leading terms. So x to the 8 wins on the top part, and then minus x to the 10 wins on bottom. So this I could rewrite as the limit as x goes to infinity of x to the 8 over minus x to the 10. So the leading terms are the only ones that matter at infinity. That's a big idea for limits. So this x to the 8 over x to the 10, we could simplify to the limit as x goes to, oh, and I forgot to write my infinity. So glad we caught that. And now we have x to the 8 over minus x to the 10 makes minus 1 over x squared. But if I had minus 1 divided by infinity squared, this is still going to 0. And it's that idea that if the denominator has a higher power of x and we're going to infinity, then the limit goes to 0. All right, now the last case is when it's a tie. Okay, if the numerator and denominator are have the same degree, then the limit is the ratio of their coefficients. And I'm just going to abbreviate coefficients. All right. So that case would look like this. Like if you had the limit as x goes to infinity of, let's say, x squared plus 1 over 3x squared plus 1. See how it's a tie, but I could use that leading term concept that I only have to look at the leading terms. So this is the only stuff that matters. X squared on top. And let's make that neater. Oh, it's taking forever to undo. All right. And 3x squared on bottom. So this is x squared over 3x squared. And now x squared cancels. This is going to equal 1/3. All right. But notice it's the ratio of the coefficients. So this is a big idea. All right. Now, differentiability. Just know if I was tomorrow's test, I wouldn't have that specific topic on there like that was done in class today. All right, so just know that's I could go over it, but it's not something that's specifically covered on the test tomorrow. All right, so just floating that out there. But if you still want me to go over it, I can still go over it. So yeah, if you want me to go over it, just say like, all right, still go over it, or pick something else from the list of topics. A random question from the derivative packet. All right. So let me just find a question from it. So that's going to take me a second. I got to open up some old, so packets of fun. Anyone in particular? I mean, I got to just be, ready to do these, but, because random, I randomly pick question 1. What if I want to be, no, I'm not going to, that would be kind of cheesy to do that. I'll make sure I got so any packet question 5. All right. So packet question 5 or 31 or 100. All right. I like, I could go over some of those. All right. So let's see. 45. All right. So we don't understand 5. So I could go over 5, and then I'll go in order of the request. So here, so we have y equals, and we have 3x to the 2/3, and we have minus 4x to the half, and then minus 2. All right. Disregard what I said. Okay. Oh, you know what I wonder? Like, I had to do a color correction to remove the screen behind me. I wonder if this will stop lagging if I have like less filters going on. But then you're going to see a green screen behind me, and it's not going to look as cool because I'm like in this. But whatever. All right. I'm just going to, that's behind the scenes stuff for me to work out. For the next one, week 3 will hopefully be better than week 2. But sometimes you have to get a little bit worse before you get better. Okay. So let's see. All right, question 5. That's where we are. So y prime. You have to know the power rule. So I'll show it kind of like in slow. Well, I have to go in slow motion because I'm lagging right now. All right. So 3 times 2/3 x to the 2/3 minus 1, which will make negative 1/3. If I'm doing this in my head, I'm going to just kind of see that when the 2/3 comes down, this 3 and denominator 3 are going to cancel like this. So I'm not necessarily writing this every single time. And then we have negative 4 times x. I'm sorry, negative 1. So we have minus 4 times 1/2 x to the minus 1/2. And then we're going to have minus 0. So now we simplify. So let's see. What are the... Oh, all right. So the answers look like they're written in fraction form. So this is going to make 2 over x to the 3rd. And 4 over 2 makes 2. And this is going to make minus 2 over x to the half. And let's just see. This is 2. Oh, all right. Well, you know what? This is written like this. 2x to the negative 3rd minus 2x to the negative half. So I was like looking through the different answers. It looks like 5 is choice E. Yeah. So, or this is the answer, but I think that matches E. All right. So that's 5. 31. All right, so 11 is before 31, so I'll just kind of scroll in order so I'm not scrolling too much. So let's see. What am I? All right, sorry, I'm trying to get this. Here we go. 31. So I'm just going to scroll. Let's see if it's something insane. I mean, challenging questions are good, but writing it when you're lagging is tricky. Oh, that one. Okay. Yeah, this is a weird question. The one where we didn't really learn the stuff yet, but sure. So this one, I think it's more about, are we allowed to use a calculator at this point? I imagine this might, is this in the calculator section? Because if not, then whatever. So 31. Yeah, so this one, it's a strange question, but 5 to the x. So this is question 31. We have f of x. Yeah, this is like a topic that we haven't learned yet, but we are going to learn before the packet is due. But we have f of x equals 5 to the x. So just to kind of gain some insight as to what's happening here, just imagine 5 to the x. Exponential function. Okay, so it looks like this. And for this one, what we have is we're in the neighborhood of x equals 1. So we know here that the 0.15 is here, but I'm going to draw in the tangent line. I believe this question uses ideas of tangent lines. And then they tell you that 5 to the 1.002 is roughly equal to 5.016. And now they're asking you which is closest to f prime of 1. So for this one, the idea is that we could write the equation of the tangent line here. But what we need to know is we need to know the slope here. So the slope, we find f prime of x. And if you have your formula sheet, this is 5 to the x, natural log 5. So now you've got the 0.15. But now, let's say we want to find the slope when x equals 1. Okay, so this is just going to be 5 to the first ln 5. But now we got to investigate a little bit. So I want to write the equation of the tangent line here. So we'd have x minus 1 times f prime of 1 is 5 ln 5. So we have 5 ln 5. And we're going to have y minus 5 equals. All right, so I want to see how helpful this is. So which is closest to f prime of 1? So now we have to make use of this somehow. Okay, so this is something we should make use of. That what they want us to do here is they want us to plug in 1.002. So like the idea being that if you plugged in 1.002 to f, you see how that's going to give you f of 1.002 is 5 to the 1.002. All right, so this is like kind of where it's guiding me. Once again, we didn't learn this yet. You know, anyone who has me, like actually has me for this. But this is the idea of kind of like what's going on here. So we plug in x equals 1.002 and we have y equals 5 and then 0.016. So if we plug those in, we're going to have 5.016 minus 5 equals 5 ln 5 times x is 1.002. So we have 1.002 and then minus 1. So now this we just solve. This is going to make 0.016 equals 5 ln 5 times 0.002. Oh, I see it now. So now you divide by 0.002, and this is going to give you an approximation for 5 ln 5, which was f prime of 1. Okay, see, this was f prime of 1. The thing we're trying to approximate. This is a weird question, but you'll see. Well, when we learn linear approximations, then this will make more sense. But then this tells you here that 5 ln 5 is approximately equal to 0.016 divided by this is 8. All right, so I believe on the packet that lines up with choice D. So that is why it's this. Wacky question. All right, so that was 31, 45, and 11. Did I do 11? I'm reading the chat as I go, and it's... Oh, you're welcome. Let's see. Let me take a look. Ah, 11. All right. Oh, I got to add a page. So much math already. So anybody else in the chat that's not a calc student, and if you have any non-calculus questions, just feel free to type in the topic if there's something else you'd like to see. So, all right, 11, we've got y equals ln, and we've got secant x plus tangent x. So this one, physics questions. I could try. I haven't taught physics in like 5 years, so it's not going to sound good. Yeah, I'm very rusty with physics. Depends on what the topic is. If you give me a topic that I know, then I have to find old lessons. All right, so secant x plus tangent x. So your chain rule variant. Know your chain rule variants. The derivative of natural log of a function is... Yeah, I mean, I could do my best to talk physics, but it's not going to sound very smart. I'm rusty. When you don't do a subject for 5 years, you really, you'll be surprised how much you forget. I mean, I know basic stuff, but yeah, sure. Throw me a topic, whatever. I'll do my best to make sense of it. It'll be like a fun exercise for me to teach something that I'm not normally teaching. All right, so it's 1 over secant x plus tangent x. So 1 over the inside. The derivative of secant is secant tangent. And then you get plus secant squared. All right, so then here is probably not going to be in the answer key, but now you factor out secant, and you've got tangent x plus secant x. And notice on bottom we have secant x plus tangent x, and that's going to cancel out this factor. See you later, and see you later. So this is just secant x. Is that an answer choice? Let's see. Yes, it is. And it's choice A. 45. So 45 is 3/4. All right. So those, you could use L'Hopital's rule. I believe that one's just 3/4. So the limit as x approaches 0 of, and we've got sine 3x over sine 4x. So if you plug in 0, you're going to get 0 over 0, which is indeterminate. So that means you could use L'Hopital's rule. And using L'Hopital's rule, you're going to get the limit as x approaches 0 of 3 cosine 3x. All right, because you're using the chain rule to take the derivative. Derivative of sine is cosine. Keep the inside 3x times the derivative of 3x is 3 over derivative of sine is cosine. Keep the inside as 4x times the derivative of the inside is 4. And now when you plug in 0, you have 3 cosine of 0 over 4 cosine of 0. There's a really nice topic, not even part of this class, but it's called small angle approximations for sine, and it has something to do with what we learn in Unit 10, but that's a ways away, so not quite, that's a little bit out of our reach right now, but stay tuned for May, or April, May. All right. So, yeah, anyone else that's here, if you're not a calc student, if there's anything not, calc related that you want to talk about, let me know. You're trying to find an unsolved physics question. Oh, just something insane that's so difficult that no one solved it yet? Or something at the high school level? Because I'm sure there's plenty of those. The unsolved ones. It's because technology keeps advancing. Let's see. 9:20. All right. So, yeah, I generally keep these between 8:30 and 9:30. So, I'll wait for other questions. But trying to find an unsolved physics question. I mean, the best thing, I would say, if you're looking for interesting physics questions, have a good night. Thank you. Interesting physics questions. You can always go on Reddit and see what the new research, there's always tons of research on that. So that's out of my zone though. I haven't been up to date on I know they did those particle accelerators and stuff, but yeah. Oh, good night. Yeah, if we have people signing out, but a calculus physics problem, I'd have to find something. I mean, the most I remember with physics and calculus is where all the formulas come from. Max height question. Oh yeah, maximum height is kind of a calculus idea. So you might remember, in physics you get formulas like this, acceleration is negative 9.81 meters per second squared. But I'll leave the units out because then in calculus you learn about antiderivatives, and the antiderivative of negative 9.81 is negative 9.81 times t, but then plus some initial velocity. All right, so this is a formula that on your reference sheet, it appeared probably like this, final velocity equals acceleration times time plus initial velocity. So I don't have the reference sheet out for physics, but I know the calculus behind it. So let's say position would be the antiderivative of velocity, and you'd have negative 9.81 times, I don't know why I made that, I turned that into a t squared over 2 plus the antiderivative of a constant is a constant times the variable t in this case, plus whatever initial position is. But usually those initial position situations where things launching from the ground, so they usually set this equal to 0. But that's why on your high school reference sheet you would have something 1/2, it would be this formula, 1/2 at squared and then plus like initial velocity times time. So this was another formula that you encountered. But once again, calculus is what makes this stuff possible, is what brings it to life. Now, this you may recognize as it's a quadratic shape. So for those projectile questions, we use quadratics to model the situation where an object is in motion. But if you want to think about the calculus behind it, an object reaches maximum height when the slope is equal to 0. But the slope of position is velocity. So that's why, like the final velocity formula, you set this equal to 0 when you are looking for max height. Okay, so this is just some ideas I remember, but the calculus behind it is what makes it make sense when you don't have a reference sheet. So set the final velocity equal to 0 when you were looking for max height. All right, but I would have to brush up on these questions. Like, not doing these for years. If I took a physics regents right now, it wouldn't be pretty. Yeah, so it's good. All right, but thank you for the question. That was a good thing to think about. All right, so any other questions here? Oh, now we got 14 people on at the same time. So thanks for the people who came by. So any other last question here before we, wrap up the live stream? I got about 5 minutes before I sign out. Can't wait for next semester. Oh, I'm glad. Differentiability. All right. Now, in terms of differentiability, I'm probably not going to go through like an entire example, but I will recap the ideas again. That when a function is differentiable is when it's smooth. Okay, and it's when it's smooth, the slope of the tangent line, let me make this thinner so it like stands out more, is that like you could find a slope at any location. And what we mean by a slope at any location is that you could find a slope of a tangent line that, let's say in this neighborhood here when the slope is 0, it's a smooth transition to 0. Like this thing it has a positive slope here, and then it starts to shrink to 0, and then the slopes smoothly transition to negative slopes. Okay, so when we're talking about differentiability, we said, like, we use the analogy of like you're looking at slope at the Ant-Man and the Wasp level. So imagine like you really shrink yourself down and look at this graph. Like let's say we really zoom in here, all right, like dramatically, really zooming in. You could see that the slope transition in this neighborhood, let's say I color code them a bit. See how it's like positive and then it goes to 0 and it goes negative. That there's no sharp turns, all right, no harsh transitions there. Okay, and the slope at any point, let's say at x equals a, is, and let's say this is x. What we have, and I'll change colors here, is if we pick a point like this, like over here, and here's a, then the slope would be f of x minus f of a, the change in the y values over the change in the x values. But in calculus, the idea is I want those 2 points to be close. Like we want those points to be super close. Okay, so we need those to be super close. And like this is at like the, like a better way of saying this, instead of super, at the infinitesimal level. Okay, so like very, 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 very close. So that's why we take the limit as x approaches a, because this means bring x and a close together. Okay, like x is getting closer to a, and as x gets closer to a, this point gets closer to that point. So if this exists, so if this limit exists, and is equal to f prime of a, let's make that neater, f prime of a, like if this is true, this implies that f is differentiable at x equals a. Okay, so what's more important than just ripping through a lot of examples? Oh, all right, so what is the difference between derivative and differentiability? That's a good question. So, and that'll be the last thing. So the derivative, let's say I have something like, I'll do a fast one. I call this one the bird function. F of x equals x to the 2/3. So the derivative is the function that tells you the slope of your function everywhere. So this function looks like this. X to the 2/3 looks like this. Okay. And you could see here the slope is not defined at 0. Like that's where the sharp turn is. So we'd say f is not differentiable at x equals 0. Third grade language, because there's a sharp turn there. Okay, so sharp turn at 0. But the difference between derivative and differentiability, the derivative is an actual function. So, and we use techniques to find derivatives. So we're going to use the power rule here. So this is the derivative of f of x. And I could rearrange this as 2/3 times cube root of x. But now if we look at this, you see how f is not differentiable at x equals 0. Notice something else, that f prime of 0 is undefined. Okay, and I'll just abbreviate, is undefined. The reason being, we would have division by 0. Okay, so when we say f is not differentiable at 0, means that the derivative is just not defined there. Okay, so differentiability tells you if, it's basically like when I hear differentiability, this basically tells me like f prime is continuous. Okay, if f prime is continuous, then our function, if f prime is continuous, then our function f of x is differentiable. Okay, so it basically tells, differentiability I also think of as where you are allowed to take the derivative. Okay, so notice like if I wanted what's f prime of 1, f prime of 1 would just be 2/3. Okay, so f is differentiable at x equals 1, and the value of the derivative at x equals 1 is 2/3. But at 0, the derivative is undefined. All right, it's a strange concept to get used to, but the derivative tells you the slope of f of x. Okay, f prime of x tells you the behavior of the slope of f. All right, cool. All right, well, it is past 9:30, so I'm going to call it a day. But anyone who stopped by, thank you so much. Yeah, I'm having fun doing these live streams. Next week, my goal is to reduce the lag. And yeah, but good night to everybody. So thanks again for stopping by. I need, let's see. Oh, all right. Take care.